Okay, so this is 5.2. Um, so here's an example that isn't too different from what we were doing in 5.1, but maybe we'd use different words to describe it. So we're given a function and an interval, x is from 0 to 2 pi, and we're going to evaluate what we call a Riemann sum with n equals 8. So a Riemann sum, maybe that's a new word, but those are the types of sums that we were doing last time. Here I graphed the function f of x equals sine x over the interval from 0 to 2 pi. I broke it up into 8 subintervals, and then I'm going to draw a rectangle in each subinterval. And the Riemann sum just means I'm adding up the areas of the rectangles. So this is really what we were doing last time. It's just that we're calling it a Riemann sum now. And by the way, just as in last time, for each interval you get to choose whatever rule you want. Well, we're being told what rule to choose here, but in general, there's various rules for how to choose the height of your rectangle. We're choosing to take the height of our rectangle at the left endpoint. So this first interval, the left endpoint is here, which means I would choose the rectangle to have a height of 0, because this is 0. For the second rectangle, my height is here because pi over 4 is the left endpoint of this interval, the interval from pi over 4 to pi over 2. And so on. The next rectangle has this height because this is the left endpoint of that interval. Yeah, and so, right, here I showed some work. I found delta x. Delta x is the width of each rectangle. The formula for delta x is always the same. If your interval is from a to b, and you're using n sub-intervals, then you just take the length of the whole interval, which is b minus a, and you divide it by how many pieces you want to break it into. So for us, that's pi over 4. And of course, that's how I knew where to draw these things where I drew them. So I'm starting at 0, and I know each rectangle has a width of pi over 4, so I just keep going up by pi over 4. So that's why this is pi over 4, pi over 2, 3 pi over 4, and so on. And I call those numbers my first one, this is the same as a, it's the left endpoint of my entire interval. That's what I call x naught, and then x1 is the next one, so that's this, x2 is the next one, x3, x4, x5, all the way up to x8, which would be the last one, because we're using 8 subintervals. Now let's talk about that Riemann sum. This is what a Riemann sum looks like. You're writing a sum. It's from I equals 1 to however many intervals you're doing, or sub-intervals. What you do is you do the height of the rectangle, which is this. And by the way, this is because we're doing left endpoints. The ith interval goes from x sub I minus 1 to x sub I, right? Like the first, I should keep calling these intervals. I should call them subintervals. I'm trying to call this whole thing from here to here the interval, and then these shorter ones I'm calling them the subintervals. I'm trying to be consistent about that, but I'm not perfect, so sorry. So the ith subinterval is this. For example, the first subinterval, when I is 1, that would be x sub 0 to x sub 1. That's this one. and then the second subinterval would be x sub 1 to x sub 2. That's this one. And because I'm doing the left endpoint, this is the left endpoint. That's why this is x sub I minus 1. If I was using right endpoints, the right endpoint would be this one, and then this would be x sub I. So it's just a slight difference. But so that's why this is what it is. And then all we do is we plug it in. We found our values of x0, x1, x2, all the way through x8. I know that delta x is just pi over 4. So now I'm going to add this up. F of x sub 0, that would be f of 0, that's f of this point. So that would be sine of 0, and I multiply it by delta x. The next one would be sine of the next, the left endpoint of the next interval. Here's the next interval, and here's its left endpoint. So sine of pi over 4 times delta x. And then sine of the next number, 2 pi over 4 times delta x. We would add this up all the way, and I didn't write it all because 8 is kind of a lot to write, but we do this all the way into the last one. The last one would be this, where we're plugging in 7 pi over 4, because that's the left endpoint of the last interval. So the last thing here is sine of 7 pi over 4 times pi over 4. And then we just evaluate it. So, of course, I can pull pi over 4 out of the whole thing, and then I'm just doing sine of 0 plus sine of pi over 4 plus sine of 2 pi over 4, all the way up to sine of 7 pi over 4. So I just do that, and actually I can do this exactly. A lot of times here we would start just using decimals. Some of these questions will ask you to round your answer to however many decimals. But in this one, we can go ahead and do it exactly. Because sine of 0 is 0, sine of pi over 4 is root 2 over 2. Sine of 2 pi over 4 is 1. And then the next one is root 2 over 2 again. So this would be sine of 3 pi over 4. Sine of 4 pi over 4 is the same as sine of pi, which is 0. Sine of 5 pi over 4 is negative root 2 over 2. Sine of 6 pi over 4 is negative 1. And sine of 7 pi over 4 is negative root 2 over 2. Notice that some of these numbers are negative. So there's something a little bit funny going on here, which is these rectangles that are underneath the x-axis, because the first ones were above the x-axis, and then we had a few that were below the x-axis. A Riemann sum counts those areas as negative, because what I'm doing to calculate the quote-unquote area of this rectangle is I'm taking the width times its height, but when I say its height, I'm saying it's a negative number. I said that the height of this rectangle was sine of 5 pi over 4, which was a negative number. So actually what happens is the positive areas and the negative areas can cancel each other out, which is actually what happens here, and we get 0. If we add all of this up, you know, there's a 1 to cancel the negative 1, there's root 2 over 2 to cancel the negative root 2 over 2. Everything cancels and we just get 0. That's precisely because the positive area rectangles and the negative area rectangles perfectly canceled each other out. So yeah, that's how you do a Riemann sum. So let's express this integral as a limit of Riemann sums. We haven't seen this notation before. This is just like saying, it's just like the last problem. Well, it's not exactly like the last problem, but it's similar enough. With this function, I just copied that from here, of course. on this interval. And I'm just copying these numbers from here and here. Oops. There we go. The different part about this one is we're going to do a limit. We don't have a value of n. On the last one we were told n was 8. N is the number of subintervals. On this one we're going to do the limit as n goes to infinity. That's what it means by saying a limit of Riemann sums. So here's what we can do. We can start doing it the same way. Delta x would be this minus this, except I don't know n, so I'll just write n. So it's 5 over n. And then I can start writing x sub 0 is the same as my left endpoint of my big interval. So x sub 0 is just 2. And then I keep going up by delta x. So for x sub 1 is going to be the same as x sub 0 if I go up by delta x. So 2 plus 5 over n. If I go up by 5 over n again, I'll get 10 over n, 15 over n. And I don't know what n is, so I have to write a pattern here. X sub I is 2 plus 5 over n times I minus 1. Wait, no, it's just 5 over n times I. Yeah, like x sub 1, I put in 1 for I get 2 plus 5 over n, and that's right. X sub 2, I put in 2 for I get 10 over n, and that's right. Okay, good. So we were also not told whether we should use left endpoints or right endpoints or midpoints or what. Let's use right endpoints, and I would recommend this in general, that this is just easier. Why is it easier? Well, we sort of discussed this last time. We said that this was, when I wrote this sum, this was an I minus 1 because we were using left endpoints, because this is the left endpoint. If we were using right endpoints, I would use this one, and then this is just x sub I. For some reason, I just find that easier. If this is x sub I find it simpler. So I prefer right endpoints. So the nth Riemann sum would be do a sum. There's one term for each interval, so I'm going to go from 1 to n, and this is going to be f of x sub I delta x, just like that one, except it was f of x sub I minus 1. So that's what we're doing. And we want to do the limit as n goes to infinity. So the limit as n goes to infinity of this sum, and then I'm also going to plug some things in. Let's see. X sub I is this, f of x is this, so I'm trying to write f of x sub I. This, what I just wrote, is my f of x sub I, right? I just plugged this into this. And then I have delta x, and delta x is 5 over n. This is my answer. Okay, good. So there's a couple of questions in this section about evaluating an integral like this by interpreting it in terms of areas. So let me draw a picture. I'm just graphing the function. This is going to be y equals x plus 1 because that's just what's in here. Of course, this is just a line, so hopefully I have enough room here. So this would have a slope of 1 and a y-intercept of 1, so it looks like this basically. Right? Yeah, obviously I didn't draw the best picture, but it'll be okay. So what this interval is representing, if I start at -2 and go up to +2, the integrals are representing area, but there's a little funny thing like we discussed about how area that's underneath the x-axis counts as negative. So let me shade, I'm going to shade the area between the graph and the x-axis. And of course, I have to shade this down here too. So this area, this triangle that's above the x-axis is going to count as positive area, and then this triangle down here is going to count as negative area. So, yeah, why don't I just call this like triangle A and triangle B. The area of triangle A, let's see, this has okay, yeah, sorry, it's 1/2 base times height. The base of this triangle would be 3, because this is at x equals -1, and this is at x equals 2. The height of this triangle would be 2. Oops. No, the height of this triangle would also be 3, because I can get the height. Of course, this is where you have to not trust my picture. To get the height of this triangle, I would plug in x equals 2, and that would give me a y-coordinate of 3. So the base is 3, the height is also 3, so I get 9/2. So for triangle B, my area is, and I'm not going to worry about the fact that this counts as negative, I'm just going to find the area of the triangle. Officially, when I say the word area, I'm always referring to a positive number. An integral involves area, but it counts certain areas as positive and certain areas as negative. So I'm going to find the area, and then I'm going to subtract, is what I'm going to do. So for triangle B, the height is 1 and the width is 1. So that has an area of 1/2. So the integral is 9/2 minus 1/2. This is 8/2, which is just 4. So that's how you do these. If it says evaluate an integral in terms of areas, first of all, you draw it and you hope that the area in question is shapes that we can calculate the area of. So triangles are friendly. We know a formula for calculating the area of triangles. Other than that, just remember that if there's any of it that's underneath the x-axis, then you have to subtract that part. You add the parts that are above the x-axis and subtract the parts that are below the x-axis. Okay, so let's do one more like that. This one. So my first step would be to try to graph this function. Let me do that. Let me first, so This 1 is just going to shift the graph up. This adding this 1 just shifts the graph up. So maybe I'll worry about what the graph of this looks like first. So what if I'm doing y equals that, this is like saying y squared equals 16 minus x squared, which is the same as x squared plus y squared equals 16. So actually, this is a circle. This is a circle of radius 4, except because y is just the positive square root, it's just the top half of this circle. So that would be the graph of just this, right? But we don't have just that, we have that shifted by 1. So let me draw a second picture, and I'll draw this one a little bit bigger because the last one was barely big enough. So it's going to be this semicircle shifted up by 1 unit. So it's sort of like this. Oops, the first part of that circle was good, and the second part's not so good. Oh well, my pictures aren't perfect. So we are finding this area. Okay, well, there's good news is that it's all above the x-axis. There's none of it that's below the x-axis, so I'm not going to have to subtract anything. So how would I describe this shape? I need to find the area of this shape somehow. Basically, if I draw this line, what I have is a rectangle down here. So it's like a short, fat rectangle with a semicircle on top. And those are two shapes that I can find the areas of. I know the area of a rectangle and I know the area of a semicircle. So the rectangle would have area, let's see, it would have a width of 8 because it's 4 on this side and 4 on this side, and a height of 1. Now the area of the semicircle, well, it has a radius of 4, and the area of a circle is pi r squared, so I'll do pi times 4 squared. But actually, this would be the area of a whole circle, and I just have half of it. So I'm doing 1/2 pi r squared. And then that's 16, so this would be 8, so this would be 8 pi. So this integral is the sum of these two. Okay.